Okay, let's dive into this. Welcome to today's Explainer, where we're jumping right into the absolute heart of grade 8 geometry. Today, we're exploring special segments, proportions, and indirect measurement. Now, if you've ever looked up at a towering skyscraper or a massive redwood tree and wondered exactly how someone figured out its height without, a giant tape measure, well, you are in the exact right place. We're going to build a geometric toolkit today that solves exactly those kinds of real-world puzzles. Here's our roadmap for this explainer. 1. The measurement mystery. 2. Triangles special segments. 3. The power of proportions. 4. Indirect measurement in action. And 5. Recap and transfer.
Section 1. The measurement mystery. Let's start with the puzzle that actually comes straight out of a standard geometry pacing guide for triangles. Imagine you're standing right in the middle of your school courtyard. Right in front of you is the school flagpole. It is way too tall to climb, and you certainly don't have a ladder or a tape measure long enough to reach the top. But your assignment is to find its exact height. So, how do you do it? This isn't just some trick question, guys. It's a completely foundational application of geometry.
To crack this, we're leaning on the core standards of mathematical practice. Specifically, we need to focus on practice 1, make sense of problems and persevere in solving them. And practice 4, model with mathematics. We are quite literally going to model that flagpole using triangles. But before we can do that, we gotta make sure we understand the anatomy of a triangle.
Section 2. Triangle special segments. Think of this as opening up your geometric toolkit, using fundamental tools like points, segments, lines, and polygons to construct some really deep relationships.
Let's pull out the first tool in our kit. A median is a segment extending from a triangle's vertex straight to the midpoint of the opposite side. Now, what's really interesting about this slide is that the median is all about balance. By hitting that exact midpoint, it perfectly halves that opposite side, splitting the triangle's area into two perfectly equal parts, no matter how weird or skewed the original triangle looks.
Next up, the altitude. This is a perpendicular segment from a vertex to the line containing the opposite side. The absolutely crucial word here is perpendicular. It has to form a perfect 90-degree angle with the base. Think about it like this. When you go to the doctor and they measure your height, you have to stand perfectly straight up, perpendicular to the floor, right? The altitude is literally the true mathematical height of the triangle. And trust me, this is going to be incredibly important for our flagpole mystery.
Our third segment is the angle bisector. Instead of focusing on the sides of the triangle, this segment divides a triangle's interior angle into two completely congruent, equal angles. It just shoots right out from the vertex and slices the angle perfectly down the middle.
And finally, the perpendicular bisector. This is a line or segment that is perpendicular to a side of the triangle, meaning it forms that solid 90-degree angle, but it also hits it exactly at its midpoint. Plus, any point lying on this perpendicular bisector is completely equidistant from the endpoints of that side. It's kind of like a combo deal. It has the midpoint finding of a median and the 90-degree angle of an altitude, but it doesn't even have to start at a vertex.
Okay, time for a pause check. I want you to actively think about this one. Go ahead and pause this explainer for a second and see if you can categorize our toolkit. Which of the 4 special segments we just defined divides an angle and which ones divide a side? Take a moment. All right, let's look at the breakdown. The angle bisector is the only one that divides an angle. Makes sense, right? The median and the perpendicular bisector both divide a side by passing through its midpoint. And the altitude? Well, it doesn't necessarily divide a side or an angle. Its sole job is to drop straight down at a 90-degree angle to give us the true height. Keep that altitude in mind.
Section 3. The power of proportions. Now that we have our geometric segments defined, we need the mathematical engine that's going to help us solve our mystery.
A proportion is simply an equation stating that two ratios are equivalent. Grade 8 standards heavily emphasize using similar triangles to explain proportional relationships. If we have two similar triangles, their corresponding sides are proportional. This basically means if we know the ratio of two sides on a small, easy-to-measure triangle, we can set it equal to the ratio of the corresponding sides on a massive, unknown triangle. It's almost like a cheat code. We use what we know to solve for what we don't.
Section 4. Indirect measurement in action. Let's move to Belize and see how this builds into finally solving our flagpole mystery.
Because the sun is so incredibly far away, its rays hit the Earth at essentially the exact same parallel angle in any given local area.
This means you, your shadow, and the sun's ray create a right triangle. The flagpole, its shadow, and the sun's ray create a larger but mathematically similar right triangle. So, step 1, you just measure your own height, your altitude, and your shadow on the ground. Step 2, measure the length of the flagpole's shadow along the ground. And step 3, set up your proportion.
Let's throw some actual numbers at this. Let's say you are exactly 5 feet tall, and you measure your shadow on the pavement, and it's 2.5 feet long. You then walk over to the flagpole and measure its shadow, which comes out to 12 feet long. We set up the proportion. Your height over your shadow equals the flagpole's height over its shadow. So 5 over 2.5 equals x over 12. Notice the relationship on the left side there. 5 is exactly double 2.5. The scale factor is 2. So what number is exactly double 12? 24. Cross-multiplying gives us the exact same result. 2.5 times x equals 60. Divide by 2.5 and x equals 24.
Here is our second pause check. We just calculated the flagpole's height to be 24 feet. Pause the explainer again. I want you to evaluate this number based on units and reasonableness. Does 24 feet actually make sense in the real world?
And the reasoning is, yes, it is highly reasonable. This is a completely crucial step in mathematical modeling. Look, if you had set up the ratio backward and gotten 0.6 feet, you'd know something was wrong. A flagpole isn't the size of a pencil. If you got 2,000 feet, you'd have a skyscraper, not a school flagpole. But 24 feet? That's roughly a 2 to 3 story building, which is the perfect size for a standard school flagpole. The math absolutely checks out with reality.
Section 5. Recap and transfer. So, the crucial point is that abstract geometric concepts are deeply tied to solving real, physical problems. Let's recap.
We started today by clearly defining the 4 special segments of a triangle: the median, the altitude, the angle bisector, and the perpendicular bisector. We then leveraged our grade 8 proportionality standards to set up equivalent ratios. Finally, we brought the whole shebang together, using our understanding of altitude and similar triangles to perform indirect measurement and confidently find the height of a tall flagpole using nothing but a shadow.
And honestly, this brilliantly illustrates the true power of geometry. But I want to leave you with one final thought to really stretch your brain. We use similar triangles and shadows to measure vertical height, right? Well, how could you use these exact same tools, proportions and similar triangles staked out on the ground, to measure a horizontal distance, like the width of a rushing river that you cannot physically cross? Think about how you might set up 2 triangles on the riverbank. Ponder that challenge, use your new geometric toolkit, and keep exploring.